So now we're going to learn how to balance equations and what those equations tell us once they are balanced. And a chemical reaction is a process in which one or more substances change into new products. The equation uses the chemical symbols to show what's happening during that reaction. And here are three ways of representing the reaction of H2 with O2. Remember that H2 and O2 are diatomic molecules in nature. They do not exist by themselves, and they will react with one another to form water. Okay, this is the space-filling model of this equation, where we have two H2 molecules, one O2 molecule that produces two molecules of water. And we can read this in two ways, or represent it in two other ways. We can represent it with words. Two hydrogen molecules plus one oxygen molecule gives two water molecules. Or the equation itself, two H2 molecules plus one O2 molecule will produce two molecules of water. And we're going to learn that this, what is called a coefficient, can also be read as moles of the substances involved in this chemical reaction. Reactants are on the left, products are always on the right. So what do chemical reaction or equations tell us? So now we're going to talk about how we read this. And I already said this somewhat in the previous slide, but here we have a chemical equation. We could read that as two atoms of magnesium and one molecule, because it's a covalent or a diatomic molecule, makes two formula units of magnesium oxide. Why does this not say molecules? Because magnesium oxide is an ionic equation. This is not a molecule. It's a compound, but it's an ionic compound. We can also read this as 2 moles of magnesium plus 1 mole of O2 makes 2 moles of MgO. This relates to the law of conservation of mass. So 2 moles of magnesium is equivalent to 46 grams of magnesium. 1 mole of O2 is equivalent to 32 grams of O2. And this reaction of those two elements, or the element and the molecule, make 2 moles of magnesium. So we get 80.6 grams of magnesium oxide. If we were to sum this side of the equation, the masses, they must equal the same mass on the other side, in the product side. So this is an example of the law of conservation of mass. What this does not say is 2 grams of magnesium plus 1 gram of O2 makes 2 grams of magnesium oxide. So coefficients give the number of atoms, molecules, ions, or moles. However, we're going to learn that Using moles, we can determine the number of grams of product produced. So first we're going to look at balancing chemical equations. And I'm going to run through this example that is given in your given by PowerPoint, and then we're going to follow this video by working on some of those reactions together. So the first thing you need, number one, is the balanced equation. So we need to write the correct formulas for the reactants and the products in an equation. Reactants on the left, products on the right. For example, ethane, if you were given a word product, reacts with oxygen to form carbon dioxide and water. So to put that into a chemical equation, we need the formula for ethane, the formula for oxygen, and the correct formula for CO2 and water. That is key. If you don't have the correct formula for the compound or the substance, you can't balance the equation. The second step then is changing or adding coefficients in front of the formulas. So how many moles or molecules of each reactant produce this number of moles or products on the right side, or the products. We never, ever, ever change the subscripts. These never change. That identifies the compound that we are working with. Okay, so let's do an example. We start then, after we have the correct formula, with the correct formulas for reactants, for products. Now we're going to start adding those coefficients by balancing the number of elements that appear in the chemical equation. So back to our example, C2H6 plus O2 giving CO2 and water. We can start with C or H, but not O. Anytime you have something that is by itself, you leave it to the end to balance the equation. And there are other rules we'll talk about as we work through some problems after this video. So we're going to start with carbon or hydrogen. 2 carbons on the left, 1 on the right. So we need 2 on the right, so that we can't lose or gain any atoms. They have to equal on both sides of that equation. So we'll multiply the CO2 by 2. So that means we put a coefficient in front of CO2. Now we have 2 carbons on the right and 2 carbons on the left. Now we look at hydrogen. There are 6 hydrogens on the left, and there are 2 on the right. So we need to multiply or put a coefficient in front of water. That is 3. So that will make 6 hydrogens on the left and 6 hydrogens on the right. Now hydrogens are balanced. Lastly, we'll look at oxygen. Now we're going to balance those elements that appear in 2 or more reactants or products. And oxygen appears both in CO2 and water. And we've got this molecular oxygen by itself. It's not coupled with any other element. So we need to total the oxygens. We've got 2 on the left, excuse me, and we have 4, 2 times 2, and 3 times 2 on the right. Flip that through. So we have 7 oxygens on the right, and we have 2 on the left. So we need a coefficient in front of O2 that will equal 7. So we're going to multiply O2 by 7/2. And when we do that, we will remove that fraction. And we have to multiply both sides by 2. So our coefficient for ethane becomes 2. Coefficient for oxygen becomes 7. Coefficient for CO2 becomes 4. And the coefficient for water becomes 6. We cannot have in a chemical equation a fraction. So we have to use a multiplier to get rid of that fraction. So we have whole numbers for coefficients. We will look at formation equations which follow different rules. But for the general balanced chemical equation, we need whole numbers. And with that, we've got one more slide to look at. We just want to verify that we have the same number of each type of atom on both sides of the equation. And so we'll run through that. We have 4 carbons and 4 carbons, 12 hydrogens and 12 hydrogens, 14 oxygens, 14 oxygens. So they match between reactants and products. Now we have a balanced equation. So next we're going to do some other examples, and we'll also talk about what type of reactions we are looking at. But that's it for balancing equations.